Coulomb's law, or Coulomb's inverse square law, is a law of physics describing the electrostatic interaction between electrically charged particles. The law was first published in 1784 by French physicist Charles Augustin de Coulomb and was essential to the development of the theory of electromagnetism. It is analogous to Isaac Newton's inverse square law of universal gravitation. Coulomb's law can be used to derive Gauss's law, and vice versa. The law has been tested heavily, and all observations have upheld the law's principle. History. Ancient cultures around the Mediterranean knew that certain objects, such as rods of amber, could be rubbed with cat's fur to attract light objects like feathers. Thales of Miletus made a series of observations on static electricity around 600 BC, from which he believed that friction rendered amber magnetic, in contrast to minerals such as magnetite, which needed no rubbing. Thales was incorrect in believing the attraction was due to a magnetic effect, but later science would prove a link between magnetism and electricity. Electricity would remain little more than an intellectual curiosity for millennia until 1600, when the English scientist William Gilbert made a careful study of electricity and magnetism, distinguishing the lodestone effect from static electricity produced by rubbing amber. He coined the new Latin word electricus to refer to the property of attracting small objects after being rubbed. This association gave rise to the English words electric and electricity, which made their first appearance in print in Thomas Brown's Pseudodoxiae Epidemica of 1646. Early investigators of the 18th century, who suspected that the electrical force diminished with distance as the force of gravity did, included Daniel Bernoulli and Alessandro Volta, both of whom measured the force between plates of a capacitor, and Franz E. Pinus, who supposed the inverse square law in 1758, based on experiments with electrically charged spheres. Joseph Priestley of England was among the first to propose that electrical force followed an inverse square law, similar to Newton's law of universal gravitation. However, he did not generalize or elaborate on this. In 1767, he conjectured that the force between charges varied as the inverse square of the distance. In 1769, Scottish physicist John Robertson announced that, according to his measurements, the force of repulsion between two spheres with charges of the same sign varied as x minus 2.06. In the early 1770s, the dependence of the force between charged bodies upon both distance and charge had already been discovered, but not published, by Henry Cavendish of England. Finally, in 1785, the French physicist Charles Augustin de Coulomb published his first 3 reports of electricity and magnetism, where he stated his law. This publication was essential to the development of the theory of electromagnetism. He used a torsion balance to study the repulsion and attraction forces of charged particles, and determined that the magnitude of the electric force between 2-point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. The torsion balance consists of a bar suspended from its middle by a thin fiber. The fiber acts as a very weak torsion spring. In Coulomb's experiment, the torsion balance was an insulating rod with a metal-coated ball attached to one end, suspended by a silk thread. The ball was charged with a known charge of static electricity, and a second charged ball of the same polarity was brought near it. The two charged balls repelled one another, twisting the fiber through a certain angle, which could be read from a scale on the instrument. By knowing how much force it took to twist the fiber through a given angle, Coulomb was able to calculate the force between the balls and derive his inverse square proportionality law. The law, Coulomb's law, states that the magnitude of the electrostatic force of interaction between 2-point charges is directly proportional to the scalar multiplication of the magnitudes of charges and inversely proportional to the square of the distance between them. The force is along the straight line joining them. If the two charges have the same sign, the electrostatic force between them is repulsive. If they have different signs, The force between them is attractive. Coulomb's law can also be stated as a simple mathematical expression. The scalar and vector forms of the mathematical equation are and respectively, whereas Coulomb's constant, the vector form of the equation, calculates the force applied on by. If is used instead, then the effect on can be found. It can be also calculated using Newton's third law. Units. Electromagnetic theory is usually expressed using the standard SI units. Force is measured in newtons, charge in coulombs, and distance in meters. Coulomb's constant is given by. The constant is the permittivity of free space in C2m-2n-1, and is the relative permittivity of the material in which the charges are immersed, and is dimensionless. The SI-derived units for the electric field are volts per meter, newtons per coulomb, or Tesla meters per second. Coulomb's law and Coulomb's constant can also be interpreted in various terms. Atomic units. In atomic units, the force is expressed in hartrees per Bohr radius, the charge in terms of the elementary charge, and the distances in terms of the Bohr radius. Electrostatic units or Gaussian units. In electrostatic units and Gaussian units, the unit charge is defined in such a way that the Coulomb constant K disappears because it has the value of 1 and becomes dimensionless. Electric field. An electric field is a vector field that associates to each point in space the Coulomb force experienced by a test charge. In the simplest case, the field is considered to be generated solely by a single source point charge. The strength and direction of the Coulomb force on a test charge depends on the electric field that it finds itself in, such that, if the field is generated by a positive source point charge, the direction of the electric field points along lines directed radially outwards from it, i.e., in the direction that a positive point test charge would move if placed in the field. For a negative point source charge, the direction is radially inwards. The magnitude of the electric field can be derived from Coulomb's law. By choosing one of the point charges to be the source, and the other to be the test charge, it follows from Coulomb's law that the magnitude of the electric field created by a single source point charge at a certain distance from it in vacuum is given by Coulomb's constant. Coulomb's constant is a proportionality factor that appears in Coulomb's law as well as in other electric-related formulas. Denoted, it is also called the electric force constant or electrostatic constant, hence the subscript. The exact value of Coulomb's constant is. Conditions for validity. There are 3 conditions to be fulfilled for the validity of Coulomb's law. The charges considered must be point charges. They should be stationary with respect to each other. The 2-point charges should be placed in a single medium, scalar form. When it is only of interest to know the magnitude of the electrostatic force, it may be easiest to consider a scalar version of the law, whereas the separation distance n is Coulomb's constant. If the product is positive, the force between the 2 charges is repulsive. If the product is negative, the force between them is attractive. Vector form. Coulomb's law states that the electrostatic force experienced by a charge at position in the vicinity of another charge at position in a vacuum is equal to, where the unit vector and is the electric constant. The vector form of Coulomb's law is simply the scalar definition of the law with the direction given by the unit vector, parallel with the line from charge to charge. If both charges have the same sign, then the product is positive and the direction of the force on is given by the charges repel each other. If the charges have opposite signs, then the product is negative and the direction of the force on is given by the charges attract each other. The electrostatic force experienced by, according to Newton's third law, is system of discrete charges. The law of superposition allows Coulomb's law to be extended to include any number of point charges. The force acting on a point charge due to a system of point charges is simply the vector addition of the individual forces acting alone on that point charge due to each one of the charges. The resulting force vector is parallel to the electric field vector at that point, with that point charge removed. the force on a small charge at position due to a system of discrete charges in vacuum is, where the magnitude and position respectively of the charge is a unit vector in the direction of continuous charge distribution. In this case, the principle of linear superposition is also used. For a continuous charge distribution, an integral over the region containing the charge is equivalent to an infinite summation, treating each infinitesimal element of space as a point charge. The distribution of charge is usually linear, surface or volumetric. For a linear charge distribution where gives the charge per unit length at position, and is an infinitesimal element of length. For a surface charge distribution where gives the charge per unit area at position, and is an infinitesimal element of area. For a volume charge distribution where gives the charge per unit volume at position, and is an infinitesimal element of volume. The force on a small test charge at position in vacuum is given by the integral over the distribution of charge. Simple experiment to verify Coulomb's law. It is possible to verify Coulomb's law with a simple experiment. Let's consider two small spheres of mass and same sign charge, hanging from two ropes of negligible mass of length. The forces acting on each sphere are three: the weight, the rope tension, and the electric force. In the equilibrium state, and dividing by being the distance between the charged spheres, the repulsion force between them, assuming Coulomb's law is correct, is equal to so. If we now discharge one of the spheres, and we put it in contact with the charged sphere, each one of them acquires a charge q2. In the equilibrium state, the distance between the charges will be and the repulsion force between them will be. We know that, and dividing by, we get measuring the angles and the distance between the charges and is sufficient to verify that the equality is true, taking into account the experimental error. In practice, angles can be difficult to measure, so if the length of the ropes is sufficiently great, the angles will be small enough to make the following approximation. Using this approximation, the relationship becomes the much simpler expression. In this way, the verification is limited to measuring the distance between the charges and check that the division approximates the theoretical value. Electrostatic approximation. In either formulation, Coulomb's law is fully accurate only when the objects are stationary, and remains approximately correct only for slow movement. These conditions are collectively known as the electrostatic approximation. When movement takes place, magnetic fields that alter the force on the two objects are produced. The magnetic interaction between moving charges may be thought of as a manifestation of the force from the electrostatic field, but with Einstein's theory of relativity taken into consideration. Atomic forces. Coulomb's law holds even within atoms, correctly describing the force between the positively charged atomic nucleus and each of the negatively charged electrons. This simple law also correctly accounts for the forces that bind atoms together to form molecules and for the forces that bind atoms and molecules together to form solids and liquids. Generally, as the distance between ions increases, the energy of attraction approaches zero and ionic bonding is less favorable. As the magnitude of opposing charges increases, energy increases and ionic bonding is more favorable.